Hello and welcome to this A-Level Chemistry walkthrough video for multiple choice exam questions. Download the questions from the link in the description, have a go at them, and then watch this video to see how you got on. Which reaction has an enthalpy change equal to the standard enthalpy of formation of lithium fluoride? Well, the enthalpy change of formation is where you make 1 mole of a compound in its standard state from its component elements in their standard states. And so first of all, if we take a look at the products, all of them are showing us lithium fluoride in the solid state, and they're all 1 mole. So there's no clues from the product side. The component elements that make up lithium fluoride are, of course, lithium and fluorine. And so fluorine is probably our first way into this question because fluorine is from group 7 of the periodic table, the halogens, and these elements are all diatomic molecules. That means they go round in pairs as F2. And what it doesn't mean is it would be an ion. And so when you make 1 mole of an ionic compound from ions, that's not the enthalpy of formation. That's something different. And so that means that we can rule out B and C because we're making our ionic compound from ions, not from the elements. And so now we're deciding between A and D. And the only difference between A and D, that's not to do with the fluorine this time. We've got half an F2 in both cases. And that makes sense because in a half a mole of F2 molecules, there will be a whole mole of fluorine atoms. And that's what we need for our lithium fluoride product. And so the difference has to come down to lithium. The lithium in D is in its solid state. In A, it is in its gas state. And the standard state for the group 1 metals, the alkali metals, is a solid. And so that means that the D is the correct answer because lithium is in its standard state, fluorine is in its standard state, and we're making 1 mole of this ionic compound. Using the data below, which is the correct value for the standard enthalpy of formation of titanium chloride in the liquid state? And we've been given the enthalpy change for a reaction of -232, and then we've been given 2 enthalpy of formation values for 2 of the compounds that appear in that equation. There's 2 ways that we can solve this. First of all, we can construct a Hess cycle from the equations that we've got. And sometimes it's okay to draw around an equation that you've been given. I've decided to redraw it in the space below here. And we know that this reaction has got an enthalpy change of -232, so I'm going to go ahead and write that above the arrow for this reaction. And we've been given enthalpy change of formation values, and the enthalpy change of formation is when you make a mole of a compound from its component elements. So if we were constructing a proper Hess cycle, we would write out very carefully what the component elements are down here in their standard states. But we haven't really been asked to draw a Hess cycle, so it's fine to just go ahead and write the word elements at the bottom here and complete the cycle by adding arrows in the correct direction. And the correct direction, when you've been given enthalpy of formation values, is to turn those elements into the compounds in the reactants and the products. And now I'm going to annotate these arrows with the values that they are representing. So the arrow that is starting at the elements and going up to the reactants, that is the sum of the enthalpy of formation of the reactants. And we've got the element carbon and the element chlorine. They have enthalpy of formation values of 0. So the only number that we need is the titanium oxide number of -912. In the products, we've got 2 compounds that are being made. So this arrow is the sum of the enthalpy of formation of the products. In other words, this value for carbon dioxide, -394, plus the value that we've been asked to find out, which I'm just going to refer to as X. And now we've got a constructed Hess cycle, we have to use Hess's law to find out our unknown value of X. And Hess's law states that the enthalpy change is independent of the route taken. It only depends on the starting and ending condition of the chemicals. And so what that means is if we're starting here at the elements and turning that into the products by going up this arrow, that is equivalent to starting at the elements still and going up this arrow and then along this arrow, and we're ending up at the same place, whichever of those two routes that we take. And so that means that the enthalpy changes for those two routes will be equivalent. And so that means that x minus 394, that's this route, will be equivalent to minus 912 plus minus 232. This then gives us x minus 394 is equal to minus 1144. And then when we add 394 to both sides, we get x is equal to minus 750. And so that means that C must be the correct answer. I said that there were two ways that we could solve this. The alternative way is to actually not draw a Hess cycle at all, and so some people might prefer this method. What we have to do though is we have to remember a shortcut that you can actually get from Hess cycles, which gives us an equation that we can remember, which is that the enthalpy change for any reaction can be calculated using the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. And if we do that, we can then substitute in the values that we've been given. The enthalpy change for the reaction is minus 232. The enthalpy of formation of the products, well, we've got our X that we're trying to work out for our titanium chloride. And we've got the minus 394 for carbon dioxide. And then in the reactants, we've got the two elements again, so those are of course 0, and we've got the minus 912 for the titanium dioxide. And then if we take the numbers on the right-hand side and we do minus 394 plus 912, which is what this becomes, we have x plus 518 on the right-hand side. And then we need to subtract 518 from both sides. So we get minus 232 minus 518 is equal to x. And then x is going to be minus 750. So we get the same answer both times, of course, and so that means that you can just choose whichever of these two methods you prefer. Two reactions of iron with oxygen are shown here. We've got the element iron reacting with half a mole of oxygen gas producing FeO, and we've got 2 moles of iron reacting with 3/2 moles of oxygen gas to make Fe2O3. And we've got the enthalpy changes for both of these. Both of them are exothermic. What is the enthalpy change in kilojoules per mole for this reaction? And the reaction involves the conversion of FeO with the presence of oxygen into Fe2O3. And the key way into this reaction is to notice that the reactants and the products for this reaction both appear in the equations above. FeO is a product in the first reaction, and Fe2O3 is a product of the second reaction. And so we can sketch out a simple Hess cycle for this situation if we put iron and oxygen at the bottom of the cycle. And then having done this, we need to show that the iron can turn into iron oxide as per the first equation above, and that's got an enthalpy change of minus 272 kilojoules per mole. But that value is for when we turn 1 iron into 1 iron oxide, and we're turning 2 iron into 2 iron oxide. So we need to double that value of minus 272. And then we can also turn those same elements into Fe2O3. So this arrow needs to go up like so, and that has an enthalpy change of minus 822 kilojoules per mole. And then having done this, we now need to apply Hess's law. And Hess's law states that the enthalpy change for a reaction is independent of the route taken. And that allows us to say that going from here to here will have an equivalent enthalpy change of going the wrong way down this red arrow. So that enthalpy change will be plus 544. And then the correct way up this blue arrow, and so that will of course have a value of minus 822. So that means that the enthalpy change will be equal to plus 544 minus 822. And then when we calculate this, we get an answer of minus 278 kilojoules per mole, and that means that B is the correct answer. Calculate the enthalpy change in kilojoules for the dissociation of 1 mole of propan 1-ol. And that's the equation that we're shown here. We've got the propan 1-ol on the left-hand side, and when it dissociates, we break all of the bonds within the propan 1-ol, and we end up with the elements in the gas state. And we've been given the mean bond dissociation enthalpy values in kilojoules per mole for all of the bonds that are present in propan 1-ol. So the first thing to note is that these are mean bond enthalpies, and so this value that we're about to calculate is not likely to be 100% accurate because the bond enthalpies are averaged over a range of different compounds. The second thing that we need to notice is that we're doing a dissociation calculation. That means that we're breaking all the bonds and nothing else. So that means that energy is going to need to go into the propan 1-ol to break the bonds. And bond dissociation enthalpies are always positive because they're always endothermic. And that means that before we do any calculations, we can rule out A and B because the enthalpy change there is a negative one, which means that they are exothermic values, and bond dissociation is always endothermic, so A and B are plausible decoys, and you can see they're just the negative of our other two options. So we're choosing between C and D. Before doing any bond dissociation calculations, I would always recommend that you sketch out the molecule that you're breaking the bonds or making the bonds within. Now we're breaking all of these bonds here, remember. And so what that means that we need to break 2 bonds between carbon to carbon, and that will each take 348. And we're breaking 7 bonds between carbon and hydrogen. Each of those will have a bond dissociation enthalpy of 412. And we're breaking 1 carbon to oxygen bond dissociation of 360, and 1 oxygen to hydrogen bond dissociation of 463. And simply all we need to do here is add those values together. And when you add all of them together, you get 4,403, definitely a positive value. The other option, C, is a decoy because if you add another 348 onto the value you get in C, you actually get the value for D. And so some people will be tricked into thinking that there must be 3 carbon-to-carbon bonds because there are 3 carbon atoms. But as you can see from my diagram, there are only 2 carbon-to-carbon bonds. And so C is correct. The table shows the standard enthalpy of formation for some of the substances in the reaction shown here. And we've got a chemical equation where ethane is reacting with 6 molecules of fluorine to turn into hexafluoroethane and 6 hydrogen fluoride. And we've been shown the enthalpy change is minus 2898 kilojoules per mole, and the enthalpy of formation is shown in this table for 2 of the compounds in that equation. We've been asked what the standard enthalpy of formation is for HF. There's actually 2 ways that you can do this. The first way I'll show you is using a Hess cycle. We've been given enthalpy of formation data. That's when you make a mole of a compound from its component elements in their standard states. Now, since we've not been asked to draw a Hess cycle, I'm just going to simplify this and write elements down at the bottom. And again, since it's enthalpy of formation, we are making compounds from their elements. And so that means the arrow to complete this cycle needs to start at the elements and then go up to the compounds. And so ethane is minus 84 and fluorine is 0 because it is already an element. So there's no enthalpy change making an element from its elements. And then for the products, the arrow goes in the same direction, starting at the elements and up to the products. We've got this, which is minus 1344, and we've got our target, which is HF, and I'm just going to call that X, the enthalpy of formation of HF. But we need to be mindful of the fact that this arrow is making 6 of those HF molecules, and so the enthalpy change will be 6X, and then add minus 1344. And so when you're using a Hess cycle, you need to know that the enthalpy change is independent of the route taken. And when we use the Hess cycle, we need to know that the arrow that contains something that is unknown, in other words, this arrow that's going up from left to top right, that arrow is equivalent to going up to the reactants and then along to the products that way. So those two routes are equivalent. And so then we need to structure this by showing that they're equivalent, and we've got 6x minus 1344, and that's this arrow here, and that is equivalent to the minus 84 minus 2898. And then when we calculate that, we've got 6x minus 1344 is equal to minus 2982. And then when we add 1344 to both sides, we get 6x is equal to minus 1638. Remember, that is 6 times the enthalpy of formation of HF. But we only want one enthalpy of formation. In other words, the enthalpy change when we form 1 mole of HF. So we need to divide this value by 6, which gets us minus 273. And so B is the correct answer. A is a sneaky decoy, and that's for if we forgot to divide our value by 6, we'd have got minus 1638, and so we'd have been thinking that A was the correct answer, but in fact it is B. I said that there are 2 ways of doing it. The second way doesn't rely on a Hess cycle, but relies on a shortcut that the Hess cycle gets us to. And that's where we say that the enthalpy change for a reaction is equivalent to the enthalpy change of the products minus the enthalpy change of the reactants. And that makes sense because what we're saying is we can go from here to here directly, or we can go down to the elements and then up the other side. We're going against this arrow, so it becomes the minus of the enthalpy of formation of the reactants. And so then when we structure it like that, we know that we've got minus 2898, that's the enthalpy change for this reaction, is equal to the enthalpy change of the products, so 6x minus 1344, minus 84 for the enthalpy change of the reactants. And so then minus 2898 is equal to 6x minus 1260, then we add 1260 to both sides, and we've got 6x is equal to minus 1638, and then x is minus 273. Of course, we get the same answer both ways. It doesn't matter which method you use, just pick the one that you prefer and the one that you find fastest to complete. In this question, we're being asked what the temperature rise is in Kelvin when 504 joules of heat energy are absorbed by 0.110 kilograms of solid iron. And we've been told that the specific heat capacity of iron is 0.448 joules per Kelvin per gram. We're going to need to use the equation Q equals mc delta T here. Q is the heat energy, 504 joules. M is the mass, which currently is 0.110 kilograms, and C is the specific heat capacity, which is in joules per Kelvin per gram. So we're going to need to convert the mass in kilograms into grams by multiplying it by 1000. So 504 is equal to 110 multiplied by 0.448 multiplied by delta T. And so then when we rearrange that, we've got 504 divided by 49.28, which gets us 10.2. And so that then needs to be converted into standard form, which is 1.02 times 10 to the 1, which gives us the answer of B. What is the enthalpy change of formation of buta-1,3-diene, which has got the formula C4H6? Well, the enthalpy change is the heat energy change when 1 mole of a compound is formed in its standard states from its elements in their standard states. And we've been presented with some data about the enthalpy of combustion of all the substances that we're going to need. First of all, I'd recommend that you sketch out the equation for the enthalpy of formation of buta-1,3-diene. And to do that, you need to write down its formula, and you need to know that it's being made from the elements that make it up. So carbon, but actually we need 4 carbon and hydrogen, and we need 3 H2s. So this is the equation for the enthalpy of formation. Now there's actually a shortcut that you can use here, but I'm going to draw a Hess cycle first. When you burn something, you form the oxides of the thing that you've burnt. So we could just sketch a Hess cycle and have oxide at the bottom, but actually I'm going to add the fact that the oxides that we would make are 4 carbon dioxide, because we're burning 4 Cs, and 3 H2Os. This wouldn't be necessary because this is just a multiple choice question. And then we need to recognise that the enthalpy of formation, which is the top arrow that I'm showing in red here, is equivalent to going down the sum of the enthalpies of combustion of the reactants, and then going up the arrow from the oxides to the buta-1,3-diene. And so the enthalpy of combustion of carbon is minus 394, but we're burning not 1 mole, but 4 moles. So we need to multiply that number by 4. And minus 286 is the enthalpy of combustion of hydrogen, but we are burning 3 moles of hydrogen. And so the sum of this arrow is minus 2,434. And the buta-1,3-diene arrow is simply minus 2,546. And so the enthalpy of formation is equivalent to minus 2,434 minus 2,546. And the reason for that is starting at the base of the arrow and going down to the oxides is minus 2,546. And so going the opposite direction for that arrow is going to be minus of that. So plus 2,546. And so the enthalpy of formation is minus 2,434 plus 2,546, which is 112, which means that A is the correct answer. I mentioned that there was a shortcut that you can use, and the shortcut is based on the Hess cycle, and that means you don't have to draw the cycle every time. And that is that the enthalpy change for any reaction, doesn't matter what it is, can be found by taking the sum of the enthalpies of combustion of the reactants and subtracting the sum of the enthalpies of combustion of the products. And you can use that for any equation when you've been given the enthalpy of combustion data. Some fuel in a spirit burner is burned and the heat produced is used to heat a container of water. In this experiment, the mass of water heated is m grams, the temperature rise is y degrees C, and the specific heat capacity is C joules per Kelvin per gram. What is the amount of heat energy absorbed by the water? Well, we calculate the heat energy absorbed by the water using the equation Q equals mc delta T. They fiddled around with some of the symbology a tiny bit here, but not much. Q is the heat energy, M is the mass, C is the specific heat capacity. It's the temperature rise that they've changed, so they haven't changed very much. Now, the temperature rise is expressed here in degrees C. However, they are tempting us to think that we need to convert that into Kelvin because 2 of our answers are to add 273 to that temperature rise. However, a temperature rise of 1 on each of the respective scales is an equivalent rise of 1 on the other scale as well. For instance, if we started at 0 degrees C, that would be 273 Kelvin. If the temperature rose by, say, 5 degrees C, that would be a rise up to 278 Kelvin. So the rises are equivalent whether you're talking about degrees C or whether you're talking about Kelvin. And so these two answers where they're trying to get us to add 273 onto the rise are immediately disregarded because we don't need to convert a degree C rise into a Kelvin rise because their rises are equivalent whichever scale you use. And so that means the correct answer is A. We have an equation that is nearly Q equals mc delta T, but they've just substituted Y as a symbol for delta T. B is probably the most plausible decoy, but we don't need to convert a rise into Kelvin because the rises are the same. The temperature changed from 21.8 degrees C to 19.2 degrees C during a calorimetry experiment. The uncertainty of each reading of the thermometer is 0.1 degrees C. What is the percentage uncertainty in the temperature change? Well, you calculate the percentage uncertainty by taking the absolute uncertainty, that's the plus or minus 0.1, and dividing it by the measurement that you've made and multiplying that by 100. If you're taking a single reading, that's the end and that's everything that you need to do. But if you're taking a measurement that requires multiple readings, and they've given us the hint here that this one does because they've said each reading, then we need to multiply this calculation by the number of readings that we've made. And so we've taken 2 readings because in order to work out the temperature change, we needed to know what the temperature began at and what it finished at. And so this calculation then has our percentage uncertainty as being plus or minus 0.1, multiplied by 100, multiplied by 2 because of the 2 readings, and dividing by the measurement that we've made, which is the temperature change. And so we're not working out the uncertainty in 21.8 and 19.2, we're working out the uncertainty in the change in that temperature. And so the difference between those 2 numbers is 2.6. And when we crunch all of those numbers together, it gives us a percentage uncertainty of 7.7%, which is precisely double the decoy answer of 3.8%. That's what you'd get if you forgot to double the absolute uncertainty.